Finally, on trial 6, it visited a new arm. So, here's why is x sub 3 equals 3? Well, because when the rat had visited 3 arms, to visit the 4th new arm, it took 3 trials, 1, 2, and 3. So x sub 3 is 3. Okay? Why am I going to all this complexity? Well, I've just shortened the table. Because if we add these numbers, 1, 1, x sub 0, x sub 1, x sub 2, x sub 7, if I add these numbers, I get 15. So the total number of trials, and you can think about that intuitively. Okay, in order to visit 8 arms, I have to visit one of them first, and then the second new, and then the third new, and that's what x sub j is doing. It's counting the number of trials before I get something new. I visit something new. Now, this means that if t, the total number of trials, is just the sum of x sub 0, x sub 1, up to x sub 7, the expected value is, applying that formula that we learned before, is the sum of the expected values. But it seems that we're going backwards. I had the problem of finding the expected value of one variable. And now I have to find the expected value of 8 variables. So am I not making it more complex? No. Sometimes you need to go downhill before going uphill. Each one will be easier. So if we could somehow figure out this simpler problem, we would be done. So let's try to find the expected value of x sub j. This means that when the rat had visited j arms, how many trials did it need on average to visit a new one? It's always good to start with an example. We don't need to be reminded of Daniel Kahneman's and Tversky's research to understand how easy it is to trip on probability. The only person that doesn't trip is the person that doesn't walk. Okay? So you have to tolerate mistakes here. Okay, suppose that the rat had visited 3 arms. So this means, and they are here in red, this means that 5 arms have not been visited in black. So I ask, what is the probability of visiting a new arm? Well, the probability of visiting a new arm is, the rat has 5 chances out of 8, so that's 5/8. What's the expected number? That's the probability. What's the expected number? That's something we have just learned. When we have an event with probability p, the expected number to get the event is 1 over p. So we just reverse this, and we get, in this case, 8 over 5. So more generally, if I visited j arms, I have not visited 8 minus j. So the probability of visiting a new arm, favorable cases divided by total cases. Expected number, just flip them around. So, what is expected value of x sub j? In the particular case, when j is 3, it's 8/5. When, for the more general case, is 8 over 8 minus j. The good thing about these general cases is that they give us the solution to x sub 0, x sub 1, because I just plug 0 here, I get, here, and I get the expected value of x sub 0. If I plug 1, so I have the general formula, basically. So, here it is. I'm repeating the expected value of t is just the sum of the expectations. Now I plug the numbers, the j value in the formula, and I get 8 over 8 minus 0. This is the average number of trials to visit the first new arm. Well, this gives 1. Of course, the rat on the first trial always visits a new arm. So this is 1. The expected number of trials to visit the second arm is 8 over 7. And you need to sum these numbers, and you get 21.74. Now, it's always nice to try to generalize. Imagine now that you have an n-arm radial arm maze. Maybe it's very big, n-arm. Well, the nice thing about when you have the general solution is that it's the same thing, except that instead of having 8 arms, you have n. Plug in the numbers, and you get this. The expected number is 1 plus n over n minus 1 plus n over n minus 2. And you factor out n, and you get this nice result. It's the number of arms in the maze times the sum of these famous numbers. 1 over 1 plus 1 over 2 plus 1 over 3. These are called harmonic numbers. Now, if n is reasonably large, and if you remember a few things about your calculus course, you know that when you're adding things that are very small and you're adding a bunch of them, it's like integrating. Okay, so this may be approximated by an integral, which is just a sum of tiny things, a sum of a large number of terms, each one very small. Well, these numbers are getting pretty small. Think about 100s and things like this. The second thing is that, so this is approximately an integral of something. What? 1 over x. And you may remember in your calculus that 1 over x gives you the log function. So we get, the approximation is basically n times log of n, plus some things like Euler constant. I will not deal with it. And you have the case here. So if you notice that the general thing, the good thing about the generalization is that, okay, a coin is just a radial arm maze with 2 arms. The same problem. A die is just a radial arm maze with 6 arms. And, well, the typical has 8 arms, but when you plug here the number of arms, and you get for a coin 3, and then for the 8 arms radial arm maze 21.7. It is always good to check your results. Let's check this one because it's easier. The problem for the coin, the equivalent problem is this. How many trials on average do you need to see both faces? Well, you flip the coin once, you're going to see one face. So, on the first trial, you always see a new face. Then, there is only one face left. That face occurs with probability 1/2. So, the number of trials on average that you need to see that second face is 2. 2 plus the first initial trial gives you 3. And I'm glad that the formula gives you 3. Okay? So we have found the solution to this problem. Summary. Very powerful technique is when you have these multi-stage experiments to break the problem in chunks, compute the expectation of each chunk, and then add the expectations. Okay? Now we're going to embark on a longer journey. This is a tougher problem. That very often in probability what scares people and what makes the problem difficult is not each step. Each step is okay, but you have many steps before you can reach the solution. Okay, so sometimes we don't have the persistence, or we don't persevere enough to get to the end. Bear with me, we'll get there. We're trying to solve a harder problem. Suppose now that D, I'm going to call D, the number of distinct arms, different arms, that the animal visits on n trials. So I'm going to fix n. Let's say I give the rat 8 opportunities. How many different arms does it visit? Well, it could be 1, it could be 2. If n is bigger than 8, I give it more than 8 trials. D can vary from 1 to 8. This is how many arms the animal can visit. So we're trying to find the probability that this random variable D equals k. What is the probability that after n trials the guy has visited, for example, only 3 arms? Or only 1? Or only 7? Okay, that's our k. This is a tougher problem. So this is our general problem. This guides us for the next 15 minutes, I hope. The solution goes like this. We're going to break the problem, to give examples and see if we can see where we're going. I don't have a recipe for this part. Fix attention on the k-specific arms. For example, on arms 1, 2, and 3. Okay? Determine the probability that these arms constitute the set of arms visited during the n trials. In other words, if we can figure out the probability that the guy visited these k arms, these 3 in this case, and only those, and then multiply that by the number of sets of k distinct arms. Multiply the probability found here by combinations of A, because I chose those 3 arms. I have 8. I could have picked another